Today we're going to talk about angular motion and constant angular acceleration. So, to start off with, we just want to understand the variables that we use when we're describing angular motion. So imagine I have some object that's spinning, like a disk that's rotating. I can look at some point on my object and I can describe the location of that object, of that point on my object with the angle uh, that it is rotated through. So imagine at some time that point is down here, sometime later it's rotated here, and we can describe how far this thing has rotated just with an angle theta. Well, the rate at which theta is changing is just the derivative of theta with respect to time, and we call that omega, the Greek letter omega. This is what we call the angular velocity. So just like when we take the derivative of position, we get velocity. When we take the derivative of angle with respect to time, we get angular velocity, and we represent that with a Greek letter omega. Looks kind of like a curly W. Now, the rate of change of the angular velocity is just the derivative of omega with respect to time, and that we call alpha, the angular acceleration. So that's a Greek letter alpha, and it stands for the angular acceleration. So just like we have position, velocity, and acceleration for linear motion, for rotational motion, we have theta. The derivative of that is angular velocity, and the derivative of that is angular acceleration, alpha. Now, if we look at how far this object has moved, this point has moved as it rotates, all right, that distance s is just an arc, a part of a circle. And we know that s is just equal to r times theta. If I take the derivative of s, that gives me the velocity that that point on my object is moving, and the derivative is just r times omega. The derivative of theta is omega, the angular velocity. So the linear velocity, the velocity of a point on my object, is just equal to r times omega. So here is a problem we can work with this knowledge. A wheel with a radius of 30 centimeters is rolling down the road with a velocity of 8.83 meters per second. What is the angular velocity of the wheel? Well, if we're in a reference frame moving with the wheel, then the wheel is not moving linearly, the ground is moving backwards, all right? The wheel, however, is rotating, and the linear velocity of the ground is the same as the linear velocity at the bottom of the wheel. And so what we can do is we can say, the position of any point on the wheel is r times theta. So the velocity at the bottom of the wheel is just r times omega, and that means that omega is just v over r, and v, of course, is 8.83 meters per second. That's the linear velocity at which the wheel is moving down the road, and then r, 0.3 meters, is the radius of the wheel. So we plug those numbers in, and we find that omega is 29.4 radians per second. There's the answer to our problem. Now, we can do problems where we have a constant angular acceleration, and they're very similar to what we did with linear motion when we had a constant acceleration. So what we do is we just say, well, look, acceleration, the angular acceleration is the time derivative of the angular velocity. That means that the angular velocity is just the integral of angular acceleration. Well, if the angular acceleration is constant, then that integral is just a constant plus alpha times t. All right? So if alpha is constant, then omega is just omega naught plus alpha t, where omega naught is the angular velocity at time t equals 0. Well, angular velocity is just the derivative of theta with respect to time, which means that theta is just the integral of omega with respect to time. But of course, if the acceleration is constant, then omega is just equal to omega naught plus alpha t. That's what we found over here. So we plug that in and we do the integral, and what we get is a constant plus omega naught t. When we integrate omega naught, we get omega naught t. And then when we integrate alpha t, we get 1/2 alpha t squared. Omega naught then is just the, theta naught is just the position theta at time t equals 0. Now, these equations look very similar to the equations we had for linear motion with a constant acceleration, but we've just replaced angular velocities with velocities, angular acceleration with acceleration, and thetas for x's. So now we can do a problem here. A car with wheels having a radius of 30 centimeters is traveling at a velocity of 8.83 meters per second. Then the brakes are applied, giving the wheels an angular acceleration of negative 0.953 radians per second squared. How far will the car travel before coming to a stop? Well, once again, my wheel is moving, and the velocity, how far the wheel has moved in x is related to how far it is rotated in theta. How far we move in x is just the radius of the wheel times how far the angle theta has changed in radians. So we can use our constant angular acceleration equation, theta equals theta naught plus omega naught t plus 1/2 alpha t squared. We're given alpha, but what is omega? What is omega naught? Well, omega naught, of course, is just V naught over R, right? That's the relationship we had earlier, that angular velocity is linear velocity over radius. So we can then plug that into our equation here. Delta x is R delta theta, but delta theta is just omega naught t plus 1/2 alpha t squared, and then we just plugged in V naught over R for omega naught. Now we just need to find the time that the wheel is moving before it comes to a stop. And to do that, we're going to use the angular velocity equation, just like when we did linear motion problems with constant acceleration. If we wanted to find the time it took for something to stop moving, we would use the velocity equation. And we're going to do the same thing here. Once the wheel stops moving, the angular velocity will be 0. So omega naught plus a t equals 0 if t is the time when it stops rotating. So we can solve that equation and we find that t is negative omega naught over alpha. But once again, we're not given omega naught, we're given V naught, but omega naught is just V naught over R. So there's our time. We plug that into our equation. Here we had time and here we had time squared. We just plug it in. Then we multiply everything out, simplify, and here's the answer that we get. And then we can plug our numbers in and get a solution. Now notice, I forgot to mention this earlier. In the previous problem we worked, there were no radians in the things we plugged in, but then our answer was radians per second. And in this problem, if you look here, meter squared up here cancels with one of these meters to give us meters. Second squared cancels with second squared. Where do these radians go? Well, radians are kind of fake units. Angle kind of doesn't have units, and when we say radians, we say what that really means is we're measuring the angle in the correct way that doesn't really have units instead of some weird system like degrees, right? So radians are more an indication that we've indicated our angles in the natural units, which have no units, more than really a unit. So radians can come and go as they please, unlike other units. So when you check your units, you can always put in all the radians you want or take all the radians out that you want. All right, there's another way we could have worked this problem. We could have said, well, look, velocity is r times angular velocity. That means that the acceleration of the car is just r times alpha, the angular acceleration of the wheel. And so then we say, well, look, if I know alpha and I know r, I know the linear acceleration, so I can just use the linear acceleration, constant linear acceleration equations, where delta x is v naught t plus 1/2 a t squared. Well, we weren't given a, we were given alpha, so we can rewrite a as r times alpha. Then we need to find the time. Well, v naught plus at is equal to the velocity at time t. If we set that final velocity to 0, we can solve for the time. Then we can plug that into our delta x equation. And when we simplify, we get exactly the equation that we'd gotten before. All right, there's one more thing I want to talk about before we finish today's lecture video. And that is that angular velocity and angular acceleration are really vectors. So if I have an angular velocity, omega, what direction does that vector point? Well, the direction is along the axis that we're rotating around. All right, so here I have a wheel and it's rotating about an axis, and so omega is along that axis. Well, which direction? There's two possible directions I could point that are both along the axis. Well, what I do is I use the right-hand rule. If I curl my fingers, so I'm going to take my hand and bend my fingers so that they're pointing, they're moving in the direction of the wheel, then my thumb points in the direction of omega. All right? So get your right hand out and try that out and see that that makes sense. Now, if the wheel's rotating the other way, then I curl my fingers around the wheel, and now omega points outward instead of inward. All right? And that is everything I have for you for today's lecture. Hope you enjoyed it.